right, so why don't we start, right? Okay, welcome to the anomaly detection in PMM. Um, I'm Daniel Guzman Burgos. I'm the PMM tech lead at Percona. Um, my specialization is on MySQL and some Postgres, and I'm kind of the observability expert, whatever that means at Percona. Um, so it's kind of funky. Maybe it's the cable. Anyway, so how many of you guys are familiar with PMM? I think everyone. So there's no need to do an introduction on that already. Great. So before stepping in on what's actually or how we are tackling anomaly detection, it's I would like to talk on what it's important to measure, or what is the things that we need to have under control on the database. And it's pretty much what your database is doing right now. And if it's what it's doing, it's okay or not, right? So when we tackle this issue, we tend to make a classification of what are like the three main tasks that the database has to do, because it's not only just execute queries. That's just the core, right? So the core is to execute queries as fast as possible, as many as possible, maintain data integrity, data quality, and then there you have the relationships. That's another thing that the database needs to take care of it, right? So that means to interact, right, with users. So databases need to have the ability to provide some sort of security with providing accounts, providing privilege to those accounts, some sort of access control, relationships with other databases, replication, foreign data access with FDW if you're using Postgres, sharding, and then relationship with actual people, devs and ops teams, right? They're if you talk with SREs or DevOps teams or even devs, what there matters, it's okay, I not only want to execute queries, but I also want to look at logs and status information. And the third thing is that database has to survive, right? That means living by the server rules. So it has to interact with the resources of the server. CPU usage, memory allocation, disk usage, all that stuff. Okay. So why we're going to focus on this one particularly, it's on the core, right? So again, queries as much as it can, as fast as possible. Let's focus on that. So how do you say that a query is fast or slow, right? Can be subjective. How we make that objective? So there's basically two things that govern the query span of life, right? So one thing is the construction of the query itself, right? The schemas that you're using, that table have properly indexes, that you're using adequate data types for, I don't know, primary keys, stuff like that. If you have much data that can be partitioned using partitions, etc., etc. That's for the query itself, right? That's a intrinsic property. The other is the availability of shared resource, right? So the query not only has to fetch some data, but also has to fight for resources that are shared. If you're on MySQL, free threads. If you're on Postgres, free process or availability of connection process. If you're on Mongo, availability of tickets for write and read. Everything related to to share access to like mutex, data synchronization when you're using distributed data, to avoid read all data, et cetera, et cetera. So these two things can be measured using the same concept, right? Time and specifically latency time. So there's going to be a latency time for the query itself and a latency time for whatever its external factors that are not related with the query. So how to know that a query is fast enough or if it's an outlier, right? And it's not the same that you have a slightly slow query than actually an outlier, right? So that's why I make it bigger. So the first approach is common sense, right? We're using LTP databases. Well, having a database that is closer to the minute than to the second, it's maybe not so good, right? We do something wrong. So, but that's not helpful enough. What about something that is less subjective, something that can be more measure and comparable? I mean, everything is related to compare, right? So again, everything is about the context. Compare the query execution time against the overall execution time of a group of queries, right? So how fast or how slow a query will be, it's actually highly tied to how the overall of the queries of the execution time behaves. How do we measure, right? So it's pretty basic statistic. There's different values or properties, right? You can use max or mean or average. Max or mean are kind of no-brainer that's not a good measure, right? If you use max, you can say my slower query max is 300 milliseconds, but then the fastest could be 289 milliseconds, still bad. If you use minimals, it's even worse. Like my faster is 1 millisecond. The slowest, I don't know, could be days. What's the problem with average? That outliers skew the value of average by a lot, right? So you can say the average execution time is 1 minute, and that probably sounds bad. And it says, wait, that's way too much time. It's very slow. But it could be that the majority of queries are taking around 100 milliseconds, but then you have this 2 or 3 that was a query for a report that it took 10 minutes, and then your average value is completely out of range. So what we should use percentile? So latency, it's not something that fits into a normal distribution, right? And when you don't have normal distribution, is that when you are hurt the most for average. So that's why it's better to use percentile, especially P99, because it will be more, it will tell more about your system. So instead of saying my average is 1 minute, but if I say my P99 is 100 milliseconds, that already rule out the outliers, right? The 99% of the queries that are being executed are under 100 milliseconds. That's pretty good, right? Instead of the average of 1 minute. And those 2 or 3 queries that take 10 minutes are just on that 1% of outliers. So that's why it's better to use this approach. It will tell more about what's going on. So in this case, anything that it's above 100 milliseconds is an outlier. You can use P85 or even P75 to narrow the fastest one, but that's like more going in depth. So now that we know what terminology or what concept it's more useful, we need to identify if it's a query is slow because the query itself is bad, or it's because it has a lot of time waiting on a queue, right? So why a query can be slow? It could be by two options. It could be both options at the same time. But that's right. It's usually one or another. So we have to talk about two types of latency: the intrinsic one and the queue latency. The intrinsic one is when the query is poorly written by itself, right? The query reads from tables that don't have a proper schema design. You're storing numbers on a bar chart or stuff like that, or you're not using properly indexes. If the query is bad, it doesn't matter if you're running on the fastest computer 24x large instance on Amazon. It's gonna take forever. So that's an intrinsic latency. How do you solve that? Query review, the classic one, explain, let's see what it's doing, etc., etc. Let's query review. Now, queue latency. Let's say the query is the most beautiful query in the world, primary keys, lookups, etc. Perfect. On ideal conditions, isolated, a good hardware profile, the query is super fast. On real conditions, that's when it's no longer on my computer works. The query is in a race of getting shared resource as fast as possible, right? Some examples. On MySQL, InnoDB rock low weights, right? The query needs to access a row, but that row is being accessed by another transaction that acquired the log before. So it has to wait. It has nothing to do with the query. It just has to wait. So that will be the queue latency. Okay. Now that we know that there are these two types of latency, how we look at that on PMM? So let's start with intrinsic latency, and that's related with the query analytics feature of PMM. So you're all familiar with this. Is this dashboard that show queries being executed and ordered by something that we call load, that it's a mix of execution time and amount of times that query has been, or that type of query actually has been executed in the period of time, in the time range that we're seeing. So that's where it's easy to see if which queries are the ones that are more slow, that you have to take care of it first, all the regular stuff on PMM. You can start with top one and see if it's a matter of it's reading way too much data to just return a couple of rows, probably a problem of indexes. It's been executed way too much time, probably a query that should be using a memory layer between the API call or whatever is in between the driver and the database. It's just subject of query review, classical query review. Now, PMM under the hood for the query analytics use a database called ClickHouse. There's way more information in the database that is shown on the regular dashboard that can be used. There, I'm not going to go too deep in details, but there we have blog posts explaining how to connect and how to get metrics. Like, well, it's pretty small, but you can have the P99 of the bucket. So how PMM when collects queries, how it group them in before it's stored on ClickHouse. It it uses a bucket of 60 seconds, right? And then it makes some sort of cluster index that it's based on the query ID, which is a hash of the fingerprint of the query. The fingerprint is the query without values. Um, and then you can see by buckets of 1 minute the P99s, right, of the query, and you can easily see if there's something that it's beyond the P99 by comparing that value with the actual executed value. Um, that's something that we will make available by default soon. But if you want to check it out now, it's something that you can do since PMM 2.0, and we're on PMMP 238. Good. Okay, what about the queue latency? That's more related with metrics, right? So some very small math definition. At the beginning, so we store metrics on a time series database, right? Time series have some sort of particularity when it's metrics that are related to time. We can use every statistic information from that, like the P99, the average, whatever. And there's this concept of Z-score that it's pretty much a math way to say how big it's something or how small it's something. Let's say we're talking about height, and the average height, it's, I don't know, I don't know in metrics, but let's say it's 2 meters, right? And then you have a standard deviation that it's a range of between the average, that something is big but not that big, or small but not that small, right? What the Z-score is how many standard deviations are you up or down from the average. Like how big are you are, or how smaller you are, or how faster you are, or how slower you are. The first approach that we had at PMM for anomaly detection was using Z-score and say, okay, how we're going to tell the user this is wrong, this is an outlier. Okay, let's use Z-score. What was the problem? Z-score needs to be pre-computed. We were using something called recording rules that make things faster. The pre-compute happens on the background, but when we tested with 2,000 clusters of Postgres and 1,000 clusters of MySQL, and it was too much. Like the latency to show the data was very high. So we took a different approach, which is seasonality. Seasonality, it's characteristic of time series in data. It could be more accurate on anomaly detection than Z-score. It takes care particular variables from a season, right? So it's not the same the workload of a database if you're an e-commerce website on Black Friday than other day, right? So numbers of that are normal on April are probably not good to give context on the peak holiday, right? Black Friday, pre-Christmas, that specific season. So instead of us putting seed scores, we're using seasonality. How are we using that? This is something that is available on the new PMM home dashboard, and it's applied right now to server level metrics. Why server level metrics? To start. So since PMM is a polyglot tool that you can monitor not only MySQL but Postgres or Mongo, or also HA proxy or proxy SQL, reverse proxy, stuff like that. So we started with the one thing that is common for everything, which is server level metrics, right? Latest PMM, the home dashboard will look something like this, and you will have some columns. That this column here, the first one, it's about anomalies. How is PMM determining that one thing is an anomaly or not? Based on previous behavior. Based on how was this particular metric behaving X amount of time ago, right? So I always use the analogy of, let's say that you're a Uber Eats or DoorDash or something like that. It's not the same traffic at Friday night that at morning 11 a.m., 10 a.m., something like that. So a CPU at 80% at Friday night could be something expected, but in Monday morning, it's an outlier. Something is wrong based on previous behavior. So what we have now, it's pretty simple. It's just, instead of these recording rules and some PromQL's calculator, we just have, I say pretty simple. It may not look like that, but it's just a calculation that takes care of the current value, the value at the same time a week ago, and what's the difference in percentage of that value, the current value, with what was happening before. Let's say that right now it's 50%, right? Last week was 50%. The difference is 0. We're good. 50% today. Last week was 25%. So that's there's a difference of 25, 50% of the same metric. There's something wrong. You should probably take a look at it, right? So Anomaly, it's all about context, right? And what we're trying to achieve with PMM is not to only show you what's going on the database right now, but also telling you if it's okay or not, right? The ultimate goal for us is that the home dashboard is just one big okay, not okay, right? And if it's okay, you move on. If it's not okay, it's gonna tell you it's not okay on this query because intrinsic latency, or because too many queries waiting for, I don't know, flow control. So maybe your MongoDB replicas are having issues, stuff like that. But always like, okay, based on previous season. It could be more complex, yeah. It could be not only last week, it could be last 3 weeks. But we decided as design just to make it as simple as possible, just the week before, as a starting point. But as you know, you can customize PMM the way you want. So we started with server level metrics. We're working on making that anomaly also on the summary MySQL dashboard. Since I just told you PMM is polyglot, so add it also to the Postgres dashboard, the anomaly detection on what it matters, right? Like queries per second or transaction per second, or I don't know if your progress amount uh, of dirty rows in a specific moment. Maybe your vacuum needs to be more aggressive, stuff like that, right? The same for Mongo. Um, the uses of write tickets, it's different. Something have changed. Um, so like I said, the idea is to apply this for everything that can be monitored with PMM currently, which is to the relational databases, the NoSQL database, the reverse proxy, Linux metrics extended. We already have that, right? Since we also had alerting on PMM, you can actually create alerts based on that type of information. So instead of having alerting on static thresholds, right? Just I don't want to get notified because CPU is over whatever value. I want to be notified if that's an anomaly value, right? That's a problem. Of course, you have to cover on things like suddenly at 99%, that doesn't matter. That's a moment that you don't care what was last week behavior is a problem. Or if you're on 10%, you're probably over provision and I don't know, losing traffic. Um, Again, something that can be customized. Uh, we do have templates for the alerting. Um, and that's pretty much it on how we are doing the anomaly detection. Um, Sorry if I rush. I thought it was take longer because we started later, but um, I don't know if you have any questions, want me to go back to something more specific. I know that there are functions on Prometheus or Victoriametry itself to do some sort of not anomaly detection, but more like forecasting. Um, but we try to go with something that it's not vendor lock. So yeah, if there are any questions, so that's it. Thank you very much for coming to the talk.